Okay. Hosanna and Bryson let me know they may not be here, so I do have a quiz, but I'm not going to give it because they're not here because of the weather. So, if they show up in the next 5 minutes, I'll give it, but otherwise, I'm just going to hold off so everybody can be here for it, because weather. So, second homework assignment is due today. The first homework assignment, I made sure it was graded by Monday, and then Tuesday being a snow day, I totally forgot to post the results to you. So I will get them posted. I get out of class at noon today, so I will do it first thing after I get out of class. Post homework 01 results. When you look at once they're posted, you go to the same place where you submitted it, and then you'll be able to view the feedback file, which will give you all the grading comments. And you should definitely look at those because a lot of people miss points that weren't necessary. There were things like, the first thing there in red, important, unless otherwise noted for credit, you must always give an explanation for how you got your answer. If calculations involved, you must show your calculation. Just having the answers will not earn you any credit. Some people just have answers without any explanation. What is the speed going to be at this time? They just put an answer with no explanation. There was another person who, said page 29. Well, page 29 is not an explanation. That's just where they were reading to get the information. You need to actually have an explanation for your answer. So, make sure you look at those and understand because we don't like taking off points. Yeah.
Can you be a little lenient with that? Because that was our first time. We were kind of confused.
Yeah, and when I asked that question, I had already done the homework and I didn't have time to go change it back before the time was up.
I will possibly go and adjust scores to be more lenient because we want learning, right? We don't want people to get low scores. But it is, in the grading of physics, it's really important to see what the thought process is, not just have answers or even, reference to a page, but the actual, reasoning. Any questions on the homework? Grace?
So the one with the horses and the guy and the
yes.
tree, I was kind of confused about that, and then I read the answer in the book and I was still confused by it. I did my best to explain it.
Okay, so let's look at this. Now I can't draw on this page. Actually, I wonder if there's a way to do it. Well, I'm not going to mess things up by trying to do it. We have 3 situations, and I'm just going to go to the lecture page and reproduce it there. So the first situation, horse on both sides. Second situation, horse on one side, tree on the other. Third situation, 2 horses in a tree. So if we go to the lecture thing, so, oh my goodness, obviously I didn't get these graded since they're sitting here. I was thinking I was one short. Now I know where they were. Okay, so the problem, page manipulation, insert, that's all we need, can be summarized as tree, green tree, rope going to a man. Okay, that was supposed to be a black, but I didn't get it black. Here, I'll make this red instead. And then going to a horse. Okay, that's my horse for today. Okay, so the horse is pulling with a specific force. That is, we have force tension equals the force that the horse can pull with. Now, if we look at the man, let's take the man and make him our object of interest and apply Newton's second law to the man. So sum of the forces on the man is equal to mass times acceleration of the man. Ideally, what's the man's acceleration here? 0. His velocity is going to stay constant, hence his acceleration is 0. His velocity stays constant at 0, but the key here is it's staying constant. So what forces are acting on the man? And I only care about the horizontal direction. So what forces are acting on the man? I've only drawn one, but it's not the only one. What else is acting horizontally? Okay, force of friction. There potentially could be a force of friction. Now for this problem, we're going to say it's equal to 0. That is, his feet are just holding him up. Right? Because, I mean, it could be otherwise. Okay, so we had force of friction is 0. What else? The what?
I was confused. I thought it was like a horizontal equal quiz. And I was actually talking about force, but like from the friction rule.
Oh, yes, I'm only looking at forces on my object. So I put the dashes around the object. Always when you apply Newton's second law, you have to define your object, and you only look at forces on that object.
The force of gravity is acting on an object, but it's not horizontal.
Right. There is a force of gravity downward. There's also a force normal upward. That's supposed to be a vertical arrow. Because he's not moving, there's not going to be air resistance. And if you want to get all kinds of technical, there's this thing we call the buoyant force. You actually weigh a little more than the scale measures because air is lifting you a little bit. When you get in water, it's noticeable. In air, it's not. So we don't count that either. Okay, but horizontal. There's one more horizontal force. Yeah, there's going to be a force of tension here as well. So we have our object here. We have all the forces, and in the horizontal direction, the sum of the forces has to be 0. So I look at my picture and I say, because I called to the right, this arrow here defined to the right is positive. When I do the sum of the forces, I'm going to take the one to the right and make that positive. So I have force tension 2. Force tension 1 is in the opposite direction of positive, so that's going to be opposite positive, negative. So in this case, the force of tension 2 is equal to force of tension 1, and since we knew the force of tension 2 is the force that one horse can make, then the tension in the rope between the man and the tree is equal to the force the horse can make. Does that make sense?
Yeah. The very last one equals force.
Horse.
It's force.
That's supposed to be an H. This is recapitulating this line right here.
Okay, yes. Let's do that.
So that's case A. Right, you have to do all 3 cases because you're asked which one is bigger, I think. So case B, what's the difference in case A and case B? Instead of a tree, you have a second horse. So for case B, I can take this and I could replace it. Oh, I wanted the black pen. There it is. With a horse. My picture's still going to be the same for the man, right? And if his acceleration is 0, then I'm still going to have that same equation at the bottom. Force tension 2 minus force tension 1 is equal to 0. And since force tension 2 is still force horse, force tension 1 it better still be also force horse. And most people would have come up with that because, well, the horse is going to make a force equal to its maximum force. So what's the difference in force tension 1 is what we're looking at. Force tension 1 in case A and force tension 1 in case B. Hint, I didn't change any of my writing. They're equal. They're both equal to the force of one horse. So A and B are equivalent. Why are they equivalent? because the man's stationary, and it doesn't matter what's pulling on this side. If he's stationary and the horse is pulling on that side, then this thing has to be pulling with a force that's equal and opposite to that. And in the case of two equal horses, it's pretty clear. Yeah, they should be pulling with equal and opposite forces. A place where people get confused is they say, but it's two horses. And so if it's two horses, then you have a total of 2 horse forces, right? You have 2 horse forces in the problem, but they're not adding up. They're working against each other, giving you a total of 0. So the man can hold the 2 horses like this. If he can hold the tree and the horse, he can hold the 2 horses. Then we get the third one because, well, you know it's not going to stay simple. So third one, I'll redraw my picture. So we'll start with the man. What color did I make the man? Red? No, blue. Blue man, like the group. So here's the man. And I'm going to put my box around him right now because he's my object I'm interested in. And there's 2 ropes. And rope 1 is going to 2 horses. And so since it's going to 2 horses, how big is the force going to be from the 2 horses working together? Now the 2 horses are pulling on the same place, so they're working together. So how big is the force going to be there? It's going to be 2 force of the horse. Now if we look in the other direction, we again have the tree. Okay, there's my tree. And so we're going to have force tension 1 going to the tree. We again must have Newton's second law acting on the man. The positive direction. And so I'm going to have force of tension 2 minus force of tension 1 equals 0 because it's still the 2 tensions acting on the man. And so I have force tension 1 equals force tension 2. But from what we had here, force tension 2 is 2 force of a horse. So in this case, the tension in each rope is 2 times the force of a horse. So this one's going to require twice the force to hold the ropes. Because in this case, the horses were working together on 1 rope. So the whole point of this is to make sure you can apply Newton's second law as I did, the black math here. That was the whole point of this problem, to make sure, and I should put equals 0 there, to make sure that you can apply Newton's second law to a situation. So, any questions about that homework problem?
So would it be incorrect if we put like CBA or CAB, like if we switched A and B?
I would just put C comma A equals B or something like that. But of course, you have to have your reasoning. That's the big part of the grade. Okay, other homework questions? Back to the homework here. Notice the typo in problem 4. Let's do problem 4 just because it has a typo. It says the box accelerates at 4 meters per second. Meters per second is not an acceleration. That's a speed. So that should be meters per second squared. So we have her pushing with 40 newtons on a 4 kilogram box, and it has a frictional force of 24 newtons and acceleration. We'll see if I remember all those numbers. Did you have a question, Jessica?
No, that was
No.
I just realized what you did.
Okay, so there's the numbers that we're given, and it gives us the answer. Right? There's no point in turning to the back of the book because it gives us the answer. 4 meters per second squared is the acceleration. We need to show that that's the answer. So how do we find from forces and mass what the acceleration is?
Use the acceleration equation.
The acceleration equation, otherwise known as Newton's second law. So we have to first identify, well, notice this picture. This picture is important for being able to do the problem because it's showing the forces I'm interested in. And I'm going to identify again that the positive x direction is that direction. And my equation, sum of the forces equals mass times acceleration, or as the book puts it, sum of the forces over mass is equal to acceleration. So if I look at this problem, I want to sum my forces. Using variables, how do I write the answer to the sum of the forces? It's what? Okay, using symbols, that's force A minus force of friction, which what you said is correct. That's 40 newtons minus 24. I ran out of space.
Why would you put, it says in the problem that she's pushing down on
Wait, it says down?
Doesn't it say it's pushing
If it says down, then I read it completely wrong. Sophia pushes with a 40 Newton horizontal force.
I added the word. I was wondering,
I was like, that makes a completely different problem.
I was wondering why you put it on the side instead of down directly. But
Okay, so sum of the forces is force A minus force F. Why is it force A minus force F, not, for instance, force F minus force A?
because you would get a negative amount.
Okay. It's not because which one's bigger, and it's true I would get a negative amount if I reversed them, but that's not the reason. That would be an outcome. The reason is I define positive as to the right. And force A is to the right, so that's why it's positive. Force F is to the left, which is negative to the right. So that's why it's negative.
Wait, so even if like force A was 24 and force F was 40, then we would still write it though.
We'd still write it this way because of the definition of which direction we're considering positive.
So then,
Do we have to explain that in our homework?
You do not have to explain that, but it's important to understand that so you don't make mistakes.
So were there any problems on the homework this time or like that where the force A was bigger than, or force smaller than force F?
Question?
So I already did the homework,
Mhm.
and I was just looking at my submission where you
You
have.
can always update your submission. You have to delete the old one and submit a new one.
I will do that on the last one because I was like, wait, I did do that right. But on this one where it says FA minus FF, don't you fill in the numbers with? Do you have to like do all that, or can you just fill in the numbers?
I will put them in. I just want to put in symbols first because I want to make sure we're clear on the directions.
So we don't have to show that.
No, you don't.
As long as it has the numbers.
Yeah, if you went straight to 40 minus 24, you'd be okay.
so if you have the picture drawn
Mm-hmm.
in your homework, but you don't have 40 on the left side and 24 on the right side, like if you have them switched,
Mhm.
is that wrong?
No, because it doesn't say to the left or right, I don't think. If it doesn't say to the left or right, and once again, I'm going back to make sure because we already had disagreement about what it said. Yeah, it doesn't say to the left or right. So you're free to choose which one is to the left and which one's to the right. Just like you're free to choose which direction you're considering positive or negative. But by convention, we choose to the right positive. I drew to the right positive. And once I've done that, then there's an order. Okay, so now we'll put in the numbers. And so that's going to be 40 newtons minus 24 newtons divided by 4.0 kilograms. 40 minus 24 is 16. And 16 divided by 4 is equal to 4.0 meters per second squared.
How do you get from newtons and kilograms to meters?
Okay, I'm going to actually come back to here. So a newton is defined as a kilogram times a meter per second squared.
Oh.
So if I take a newton, divide by a kilogram, the kilogram is going to cancel. I'm left with a meter per second squared.
Oh, okay. So when we put it in our homework and we automatically write it as meters per second squared, because that's the answer that we were given, do we have to explain the Newton part?
You don't have to explain it. Best practice is to put the units into your calculation like I did, and then the units work out. In your class, I'm not going to mark you wrong if you don't write the units as you're doing the work, but sometimes you'll get the wrong value if you don't pay attention to the units, so it's a very important thing. Okay, let's move on with the material of the day. So work. I ended last class period, which seems like forever ago, with the definition of work. Work is force times distance parallel to the force. So if I have this mass, what direction is the force my hand is putting on, on the mass?
What direction?
Yeah, what direction is the force my hand is putting on the mass?
Isn't it going down?
My hand's pushing up. Force of gravity is pushing down on the mass. The mass is pushing down on my hand. I'm pushing up on the mass. So the force my hand is putting on the mass is upward. Now if I walk like this at constant speed, so I have no horizontal force once I get it going. Since my force is vertical and the velocity is horizontal, how much work am I doing? Not that much is an understatement. 0. Because work is only done if the motion is parallel to the force. So since my force is vertical and the motion is horizontal, they're perpendicular. There's no parallel parts. Likewise, if I set this on the table, there's no motion at all. There's force holding it up, but there's no work because the force is not making it move. But if I take it and I raise it, then I did work on it because my force was up and the distance it moved was up.
So then, if you're applying like a force of friction, it's moving horizontally, then it would work.
So, well, let's use friction here as a practical example. If I push on this, I'm pushing right now softly. It's not moving. How much work am I doing? Doing none. Is there a force of friction on this?
Yeah.
Yes. What direction is it pointing? It's pointing opposite the direction I'm pushing to keep it from sliding. Is it doing any work? Why not?
Because you're not pushing it.
Well,
There's no distance.
I'm pushing. You may have added a modifier to it. I didn't care. If you said you're not pushing hard enough, I'd say, well, sure, that's good. I'm pushing, but I'm not pushing hard enough to make it move, and so there's no motion for the force of friction to do work, just like there's no motion for me to be doing work. Now if I push it starts to move, am I doing work on it? Yes. Is force of friction doing work on it as it slides? Yes. Okay, now the last part of this sequence, am I doing a positive or negative work when I'm pushing it? Positive, because my force is the same direction it's moving. So is friction doing a positive or negative work on it as it slides? Negative, because the force of friction is the opposite direction that it's sliding. Now when your car accelerates, remember force of friction is what's making it so it can move. The force of friction is pointing the same direction it moves. It's doing a positive work in your car in that case. Okay, so that that idea of parallel and having motion, those are two really important things. If you push against the stationary wall for several minutes, do you do work on the wall? Do you do no work on the wall? Do you do work on the ground?
No work on the wall.
Okay, no work on the wall. Why not?
Because there's no motion involved.
Okay, no work on the wall because there's no motion involved. What about work on the ground? Not moving, so there's also no work on the ground. So the correct answer is B. Right? We have to consider C as well, just because they're not necessarily exclusive. So I think we've got that down.
If you were pushing on a wall and you had, like, on a hardwood floor and you had the socks on and that was causing you to slip, then would it involve work?
Then if you're sliding, then the force of friction is going to be doing a negative work on you, and the wall is doing a positive work on you. Yeah. Now, the reason I actually have this question here is tying into the next part. When you go and work, you should get tired. I used the snowblower this morning instead of the shovel, so I didn't get all that tired, but I did some work and I got a little tired. Right? That's the way it works, right? Do you get tired when you push on the wall? And so the way you're thinking then, that should say, I did some work. And so we have to be careful with our definitions here. What I'm talking about in work in this class is what technically is termed mechanical work. Mechanical work is work that makes things move. If I am pushing on a wall or doing something like, holding this in my hand, as I apply a force, I am using energy. My body is doing chemical reactions to convert energy from one type to another, and so I start getting tired as it goes on. So if this is not very heavy, I can hold for a long time. But eventually I get fatigued, have a hard time holding it up because of all of the work, biological work, my body's done. That's not what we're talking about in physics. We're only talking about mechanical work. And an easy way to think about this, I'm not going to do this example. It'll obfuscate the point. Let's just go forward. So energy is defined as that which produces changes in matter. That makes a lot of sense. Define change in matter. Okay. Energy is the ability to do work. If something has energy, it has the ability to do work. And so there are different ways we can have energy. For instance, if I take this mass and I hold it above my head, and then I let go, what will happen?
It will hit you in the head.
Well, I'll keep it not over my head. But it will fall down, right? If it falls down, there was work that was done on it. There was work that was done on it by the force of gravity, because gravity knows the force that was pulling it down. If it falls down, there was force times distance, there was work. And so we say that this has a potential energy, based on its position. Potential energy is the ability to do work because of something's position. We also have things like, if I had Amber stand up in the middle of the room and I went running at her as fast as I can, when I hit her, would I do work on her? Yeah, I would do work on her. There would be a force. There would be a force when I hit her, right? And she would move because of that force. So there would be work done if I went flying into Amber. And that energy, the ability to do work, was because I was moving. And we call the ability to do work because of motion, kinetic energy. Kinetic means moving. So we have two types of energy: kinetic energy, ability to do work because of motion; potential energy, ability to do work because of position. Now here's something important. Both work and energy have units of joules. That's pronounced joules, dude's last name. And so if we look at our work equation, it's force times distance. I put delta x because that's change in position. And I'll put this little parallel sign to say the position change has to be parallel to the force. If we look at the units, what are the units of force? Newtons. And what are the units of distance? They're meters. And so the units of work are newtons times meters. And so a joule is equal to a newton times a meter. Now going back to Amber asked how I got meters per second squared from Newton's second law. And I reminded you that a newton is a kilogram times a meter per second squared. So I take that multiplied by a meter. So that's kilogram times meter squared per second squared. So the unit of a joule is a newton times a meter, or a kilogram times a meter squared per second squared. It would be kind of a nuisance to go around writing kilogram meter squared per second squared all the time. That's why we have J, which is much shorter to write. So J is the abbreviation for joule. You can see I used it without even thinking because I've been doing this stuff longer than you guys have been alive. But J is our symbol for the unit joule. So when I talk about energy, I'll say it has this many joules of energy. So let's talk about power. Power, I'm not going to ask you what it means. We might get some right answers, we might get some wrong answers. Power is a rate. We've learned about other rates. Can you name something else that we've used in this class that's a rate?
Isn't it velocity?
Okay, velocity is the rate of motion. Rate means per time. So velocity is the motion per time, the distance per time. We also have acceleration. Acceleration was the rate of change in velocity. So it was the change in velocity per unit time. So now when we talk about power, power is the rate of energy conversion or work done. So that means it's going to be the work done divided by the time it takes. So power is a number telling you how quickly the work is done. High power means the work is done quickly. Low power means it's done slowly. Now, if we look at the units here, power is equal to work over change in time. That's going to give us units of work was joules. Time, what's the unit of time? Seconds. So joule per second, which we call a watt. So power is in units of watts. Now, joules per second is not very hard to write, but we still use watts because we use them all the time. Now, remember, a joule is a kilogram meter squared per second squared. Then we divide that by seconds. So that would be kilograms times meters squared per second cubed is a watt. Second cubed seems really bizarre. You have to keep things in perspective here and not try to figure out what's a second cube, because there is no such thing as a second cube. But what you have is divided by units of time 3 different times. Once to get to speed, once to get to acceleration, and then once to get to power. So our units for power, watts, but you need to understand what the watt is and not just some magical thing out there. So a job can be done slowly or quickly. Both may require the same amount of work, but different amounts of Okay, so we have disagreement. One person says energy, one says power. Remember, energy is the ability to do work. So it's going to have to require the same amount of energy to do the same amount of work. So if the same amount of work is going to be the same amount of energy. Momentum. What is momentum? Rate of not rate of acceleration. It's mass times velocity. It's the mass times the rate of motion if you want to use the word rate. It's mass times velocity. That's just not it. It's a different idea. Power. What's power?
Work done over time.
Work done over time. Well, we have different times but same work. It means it's going to be different powers. Final answer here, impulse. What is impulse? Now notice some confusion. Momentum is P equals mv. Power is P equals W over delta T. Impulse is delta P. What's the difference in the P's? There is a difference. It's really hard to note when it's written. Power is capital P. Momentum is lowercase p. So while those look like the same things, these are not the same P. This is a capital P. Here, I'll put an underline to indicate it's capital. And the others are lowercase. This, of course, illustrates one of 75 million times how it can be confusing dealing with our physics symbols. You really have to know what they mean in order to be able to use them, and there's a lot of potential ambiguities. Do you have a question, Lindsay, Jessica? No. Just want to make sure you're not like, he said this, I thought, now he said that, type thing. Okay, so potential energy. I already talked about potential energy. I said it was the ability to do work because of position. So if we have a ball up here, it has a certain amount of potential energy that it can do before it hits the floor. That potential energy is going to be the force of gravity. What's the equation for the force of gravity acting on this?
Like mass. Something has mass.
Has mass. Mass times. Not weight. The force of gravity is the weight. Mass times the acceleration of gravity. Sometimes people say mass times gravity, which is really not good because gravity is a bigger concept. It's not the acceleration of gravity specifically. But mg is perfectly acceptable. So it has a downward force that's mg, and then the work it can do is going to be that force times the distance it could fall. So it'd be mass times gravity times the height. So in this picture, we have 3 balls. Each ball has a weight of 10 newtons. And each one has a height. I was going to circle the 3 because it's 3 meters. Has a height of 3 meters. So in each case, the potential energy of the ball is 30 newtons times meters. What's the way we usually write joules? So in each case, the potential energy is 30 joules. And now our picture shows the ball going down the ramp, going straight to the ground, or going down the steps. If, and this is a big if there is no energy lost as it falls, then all of its potential energy will have been transferred out. It will have done work. And so they should all have the same amount of work done on them by gravity to get to the bottom. Now, in fact, gravity is going to do the same work in all cases, but you're going to have some slight differences in the net result, which just complicate things. So other examples of potential energy. We had potential energy due to gravity is mass times gravity times h. We also have potential energy in a spring. If I take a spring, like this slinky, if I stretch the slinky, if I let go, the spring will pull it back together. So that means there was a force to pull it back together, and it came together. That's a potential energy. And so a spring can have a potential energy. The equation for it is potential energy for a spring is equal to 1/2 kx squared, where x is how much you stretched it. And k is called the spring constant. It tells you how stiff the spring is. The bigger k is, the stiffer the spring is. We're not going to go any further than that, just saying that we can have potential energy in those. The top one is a cool one, bow and arrow. I don't know about you, but when I was a child, one of the things I liked to play with was making bows and arrows. So we'd go get sticks, and we'd love to make them out of eucalyptus sticks because they seem to bend better. And we would tie completely non-stretchy string to it, and then we would find sticks that seemed pretty straight, carve them to try to make them straight, or make arrows. We had bow and arrow. And if you're really lucky, you might be able to shoot an arrow from here to the back of the classroom. Very ineffective. But those are examples of an energy device. When I take that bow and I pull on the string, I'm causing the bow to flex. I'm doing work on the bow. And as I do that, the bow starts storing potential energy because it's bent. And then when I let go, it springs back and returns all of that energy, giving it to the arrow. So it does work on the arrow, making it move. So a bow is storing energy.
Wait, can you go back for just a second? What is the S? Is that supposed to be an S that's next to the potential energy?
Yeah, that's S for spring.
And then that's X next to the K.
That's X next to the K, yes. Okay, we've actually already talked about the gravitational potential energy, so I don't need to go into that anymore. The work energy theorem is going to be the last thing I think that we have time to talk about today. The work energy theorem tells us about the relationship between work and energy. Now, I said energy is the ability to do work. Well, the work energy theorem gives us an equation for that idea. And that equation is actually real simple. Of course, I say it's real simple, and then I write things that don't mean anything to you. So let's start right at the very beginning. I put W. What does W stand for? Work. I put a subscript of net. What does net mean? Not forces this time. What did it mean when we did net force? Net means you add them all up. So work net means you add up all of the works. So you can have work, in my example here, I had work done by friction and the work done by my finger. So you add those up. So I had one was a positive, one was a negative. You add them together. That's what the net work is. Then I have a delta, the triangle. Greek capital delta. What does delta mean? Change it. It's always final minus initial. And then I have something completely new. KE. I've used the words kinetic energy. So the net work is equal to the change in kinetic energy. But at this point, we don't know what kinetic energy is. So it's kind of hard to put that into something practical if we don't know what kinetic energy is. So we have to identify kinetic energy, the energy something has because it's moving, has an equation that we get through calculus of 1/2 mass times speed squared, or if you prefer, p squared over 2m. Is that a capital or lowercase p? Lowercase. Right, I made sure that it crossed my division sign, so you would recognize it's lowercase p. What does lowercase p stand for? Momentum. So kinetic energy, 1/2 mass times speed squared, or momentum squared divided by 2 times the mass. That's the kinetic energy. So if I have something that's doing work on something, it's going to change that kinetic energy by amount equal to the net work. So we have this picture again of the guy in the car hitting the brakes before he goes over the ledge. He has a kinetic energy 1/2 his mass times the speed squared. And he's going to have to get enough work done to bring his kinetic energy to 0 before he goes over the cliff. And so the work he needs done is going to be, he needs his final kinetic energy to be 0. His initial is 1/2 mass times speed squared. So he needs a total work done, a net work done, of 0 minus 1/2 mv initial squared.
So when you're writing it, like if his starting thing is, or if it's, do you write the final minus initial?
Always final minus initial. So it's going to be a negative change in kinetic energy for him to go from moving to stopped. And so the net work needs to be negative. For the net work to be negative, that means the force and the distance have to be opposite directions. So the car is traveling to your right, the force is going to have to be to your left. That gives you a negative work because the force is opposite to the direction. And in this case, it's going to be what force is going to stop the car? Friction, yes. So force of friction, now I'm switching from the guy to the entire car. So 1 minus 1/2 mass of the car times speed initial squared is what we need. It's going to be equal to the force of friction times the distance. If you have a large force of friction, how much distance are you going to need to brake to stop? If you have a large force of friction, it's a smaller distance because the work is force times distance.
But isn't it like when you have like a semi-truck, you need longer to stop than like a little car?
Yes, that has more mass.
Oh.
Right, the kinetic energy is going to be bigger because of the mass. But I said if the force of friction, the stopping force, the bigger the stopping force, the smaller the distance you need. Which is why we like to have good brakes. So hey, look, there's the equation we just did. Small changes in speed, large change in kinetic. Yeah, whatever. Wait a minute. It depends on the mass for this relationship. Small changes in speed produce large changes in kinetic energy. The thing that this line is trying to emphasize is that speed is squared. So if you double the speed, you have 4 times the kinetic energy. That's what that statement is trying to say. It's not, I took it from the textbook, right? It's not the clearest statement in the world, but this is, momentum was mass times speed. This is mass times speed squared. So this is more affected by the speed than momentum was. So back to the work energy theorem, net work is change in kinetic energy. If there's no change in an object's energy, then the net work has to be 0, right? Now, yeah. let's just look at this example and be done. So an example of this, if I have a pile driver, the pile driver is you have that big mass and you raise it up. So you have that crank that somebody was turning on doing work because they were applying a force on that crank. They moved it a distance parallel to the force. They did a work. And as they did that work, it changed the energy of the mass. The mass went higher and higher and higher, which means its potential energy went up, up, up. So they were putting a positive work in, and the potential energy went up. Then you cut the string, and gravity takes over. Gravity's going to make it fall. And we've learned that gravity is going to apply a force of mg over the distance d that it falls. So gravity is going to do a work of mass times gravity times the distance it falls on. And then it hits this post, and all of that energy that gravity did on the pile driver, on the mass, is transferred into the post, puts a downward force on it, and the earth is resisting. But because you have energy being transferred, it's going to have to move so that the energy can be transferred. So you have the force times distance taken out by the friction between the post and the ground. So the pile driver is transforming energy. And I'll try to do a cool demonstration of this beginning of next class period. Remember, homework is due today.